So last time I talked about expanding continuous time functions or signals in terms of complex exponentials, just like we did in discrete time. X is periodic with period p, and omega naught is the fundamental frequency. So I'm assuming p is the fundamental period. Okay? The main thing that's changed up to this point is that our summation is now infinite. Anytime you have an infinite sum, you have to worry about things like convergence. But we're not going to worry about that in this course, because it will clutter the main concepts, which is how to break down signals into their individual frequency components. The frequencies that are present in a periodic signal in continuous time, frequencies that contribute, that can contribute, are only 0, plus minus omega naught, plus minus 2 omega naught, and so on. So I should say are only, or include only. There is no other frequency aside from this discrete countable set that can contribute to a periodic signal. And that's the counterintuitive part of this whole story that I mentioned last time, got Fourier into trouble. And this expansion essentially says I can take a whole bunch of complex exponentials. Each one of these contains a pure frequency, a single frequency. So the kth term contains frequency k omega naught. And its contribution to the overall signal is measured by the coefficient in this expansion. The larger the magnitude of this coefficient, the more this contributes to the overall signal. And so you've got a whole bunch of these, in fact, an infinity of these theoretically, that contribute to the signal x. And our job now is to figure out what the expression is for each of these coefficients. X sub k's describe the frequency domain behavior of the signal. The kth term tells you how much of frequency k omega naught is present in the signal. So each of these is associated with a coefficient, x sub k. This one with coefficient x sub 2. Oh, I should say xk and x minus k, the way I've written it. x2 and x minus 2. x1 and x minus 1. And x0. So what we want to find is the expression for each of these coefficients, and then we're done. This is the synthesis equation. You've already seen the synthesis equation. It's the one that tells you how to break up a signal or how to synthesize a signal by linearly combining complex exponentials. So x of t, I'll rewrite it here. Overall k, x sub k e to the I k omega naught t is the synthesis equation. And we're after the analysis equation, the one that tells you how to express xk in terms of xt. This would be the analysis equation. Well, we do exactly what we did in the discrete time story. We have x of t that we can represent as a linear combination of a bunch of these functions that are now functions of a continuous time variable, continuous variable t. Okay? Where the ck is that kth complex exponential. In discrete time, there were e to the I k omega naught n. Now we just have e to the I k omega naught t. We're going to show that these CKs are mutually orthogonal. So there is a compact way of writing it, and that whenever these indices are the same, you get the number p. Exactly like in discrete time. We will show this. So that means CK is orthogonal to CL for K not equal to L. And CK magnitude squared is simply P. Now, what this inner product means in this context is something that's new. We have to redefine our inner product in order to be able to talk about this whole story in continuous time. The inner product that we defined in discrete time is not going to work. Okay. Well, for now, assume that this relationship holds. I don't want it to bog down the main part of the discussion. If this relationship holds, in other words, if these complex exponentials are mutually orthogonal, you can think of them as vectors that are orthogonal in some sense that I will define, then how do we find the coefficients? What was our methodology? If I want to get rid of some of the clutter, I'd write x is equal to a linear combination of a bunch of these vectors. Okay? How do I find x sub k? What is it that we did in discrete time? Inner product with one of these functions. So let's say I take the inner product with the Lth term. Then on the right-hand side, how many terms are non-zero? Which one? Which one? The Lth one. So on the right-hand side, you'll have XL psi L. XL psi L, psi L. Right? All the other terms, because these happen to be orthogonal for other indices, all the other terms go away. The only one that's non-zero is this one. X sub L is a constant. I can pull it out. And so now I have an expression for the Lth coefficient. And again, this magic equation shows up in our derivation. Notice how quickly we got here. And if you don't like L, the kth one is simply the projection of that infinite sum over the kth vector. And what do we have in the denominator that I haven't yet proven? P. So I have a 1 over P x ck or psi k. Again, we get back to this question, what the heck is this inner product? How do we define this inner product in continuous time? Well, let's go back to what we did in discrete time. If I had two periodic functions, f and g, periodic, in fact, they're periodic with period p. So they're p-periodic. How did we define the inner product? Sure, I can use F transpose if you want. G conjugate, which ended up being, if I look at one interval or one period, it was what? F of n, G conjugate of n. Okay? Now you have functions not of n, which is an integer, but of t. So how would you change this? In continuous time, if f and g are periodic with period p, I heard an integral. Huh? Integral over what? 0 to p or any interval of length p. So, or, in general, you have a choice of what interval to pick. So this represents any interval of length p. Just as you could here. It doesn't have to go from 0 to p minus 1. It can go from minus 1 to p minus 2. It can go from 1 to p. Whatever you pick, as long as you pick one period, you're good. And same here. So examples are, of course, 0 to p, or minus p over 2 to p over 2. These are usually the two intervals we deal with. But any interval of length p will do. Whatever is convenient. Okay, so f of what? T, g conjugate of t dt. By the way, it doesn't take a whole lot of imagination to think that if we move beyond periodic signals and you want to take the inner product of, say, two non-periodic continuous time signals, what's going to change? The integral now goes from minus infinity to infinity. Okay? So it's this definition of inner product. Notice we started with what you knew from high school about dot products of vectors. And then we generalized it to continuous valued vectors. Then we moved on to functions and now to continuous time functions that are periodic. And then you can go to non-periodic functions. Okay? So if this is our definition, then x inner product with ck must be what? I'm going to pick an interval, whatever is convenient. Tell me how to fill this. X of t ck star, which is what? E to the negative I k omega naught t dt. Okay? And now we have our equation, our analysis equation. It's 1 over p integral over 1 period of x of t e to the minus I k omega naught t dt. And this is the analysis equation. That's it. These are the two equations for Fourier series in continuous time. The synthesis and the analysis. Yeah? Yeah, so I haven't gotten there yet. This was all premised on this assumption. Now, just so that Ali doesn't feel like he's been cheated, we'll do the orthogonality. Well, actually, let's do the same index. Well, we can do both in the same go. Let's do ck cl. So this is integral over 1 period. Pick the period. Let's say 0 to p. ckt cl star t dt. So it's the integral over 1 period, e to the I k omega naught t times e to the negative L omega naught t dt. You have a product of two exponentials. One of them has a negative sign in the exponent, and that's what you get. Remember what I said about exponentials showing up in summations or integrals. Exponentials that may become 0. So you've got to consider two different cases. K equals L, and k not equal to L. What happens if k is equal to L? What happens to the integrand? You're integrating from 0 to p of 1. And what does that give you? P. So far, so good. We said that if k is equal to L, you get P, just like you did in discrete time. This, of course, corresponds to, well, with functions, I can use 1 bar. Now, when k is not equal to L, I don't have to write anymore. I just have to argue it on this expression. When k is not equal to L, how do we argue that this is going to give us 0? Well, maybe one step will help. I'm integrating from 0 to p. This complex exponential can be written as a cosine and a sine. Remember Euler's? I sine k minus L omega naught t. Let's make that a curly bracket. dt. Okay? Let's look at each of these terms. This first term. What kind of a function is this? Periodic. With period what? P. I'm integrating a periodic function with period P over one period. And this is not just any periodic function. It goes up, and then it comes down. It spends as much above ground as below ground. So when you integrate over that one period, in fact, this, if k minus L is 2, 3, 4, or any integer larger than 1, this will be periodic with a fraction of the period p. So if k minus L, for example, is 2, this cosine undergoes 2 complete cycles in this interval. If k minus L is 3, this cosine undergoes 3 complete cycles in one interval. Whatever the integer difference is, this thing undergoes an integer number of cycles in this interval. So when you integrate, what do you get? 0. And the same is true for the sine. And you're done. Okay? As I mentioned last time, there are a lot of subtleties that I'm sweeping under the rug. You've heard me say this before, that your education is a process of what? Huh? Let's see, who's the optimist, who's the pessimist? Huh? Progressively diminishing lies, if you're a pessimist or a cynic. Or successive refinement, if you're an optimist. So there are certain things that we're sweeping under the rug. I spoke about one of them, namely that when we say x is equal to that linear combination, we're not talking about a pointwise equality. In fact, if your function x has discontinuities, you can't construct the discontinuous function by linearly combining a bunch of continuous and infinitely differentiable functions. The complex exponentials are infinitely differentiable. They're smooth. You look at the real part, it's smooth. You look at the imaginary part, it's smooth. You can't combine a bunch of smooth functions and get a discontinuous function. It's not possible. So that equality needs to be viewed with a grain of salt in a particular way. But essentially what it means is, if you look at the error signal, if you subtract one side from the other, and you have an infinite number of terms in that summation, the energy of that error signal is 0. And real-world systems care only about energy. But that's something that we'll we'll deal a bit more with next semester in 120, or whenever you take it. The instructor will deal with it. Let's do some examples. The square wave? Yeah, so the square wave has discontinuities. No, but the square wave, if you evaluate the right side with the square wave is my second example. Let me do the first example and we'll get to this. We did the infinite impulse train in discrete time. Let's do that in continuous time as well. So this is my periodic signal. I want to figure out what the coefficients are in the Fourier series expansion of this thing. What are the xk's? Notice there's a reason why we put these k's as the index. Because in general, whatever expression you find for the xk has some kind of a k dependence involved. But in the case of the infinite impulse train, it turns out this function, or this signal, takes an equal contribution from all frequencies. So how do you find the, We're about to get to that conclusion. We don't know yet. Well, we did it for discrete time. So you kind of expect it in continuous time. What would you like to pick as your interval of integration? 0 to p. What else? Negative p over 2 to p over 2. I'll go along with that. You don't want to start your interval on the boundary or on the point where you have an impulse. I mean, if this thing had been something of a finite height, that would have been okay. But when we're dealing with a generalized function like the Dirac delta, you don't want to start your interval from there. Unless you're very clear that you're starting it immediately to the left of 0 and going to immediately to the left of p. But why worry about all that when you can just pick this interval? And you don't have to worry about the number of impulses that fall in that range. So when I look from minus p over 2 to p over 2, what do I see as x of t? What does x of t look like when I look at this? Dirac delta. And I have e to the minus I k omega naught t dt. And what do you know about the Dirac delta when it comes in contact with another function and then integrate it? Sifting property. So it takes up the value of this exponential at what location? At 0. And what is that value? 1. So this whole integral is 1. Equals 1. And you're left with 1 over p. Now Muhammad is happy. So this expression for x of k says the infinite impulse train can be written as 1 over p times all these complex exponentials, the sum of all these complex exponentials. Each frequency k omega naught contributes equally. I have the same coefficient for all the frequencies. This impulse is the prototypical example. It's the ultimate in narrow in time functions. You can't get narrower than that. It's narrow, its width is 0, but it has finite energy in it. I'm sorry, it's got finite area. But in frequency, it expands all over the place. From minus infinity to infinity, it contains all the integer values of omega, integer multiples of omega naught that you can imagine. And it contains them in equal amounts. Now let's go to the square wave. By the way, in answer to your question, you have the same problem here. At 0, at non-zero values, what happens? So anywhere you have a discontinuity, you're going to run into trouble. But it becomes more pronounced, actually, in this situation. So here I have a function of time 0. Let's say it goes from minus t to t. This is the square wave. It turns out that the value of the, when you plug into the synthesis equation, the right-hand side gives you a value that's half the height at the discontinuity. It's not equal to that. And it's not equal to that. It goes like that. As you increase the number of terms, this boundary becomes sharper and sharper. But at exactly that boundary, it's at the halfway point. That's, again, part of the subtleties that we don't really go into in the class. But find me the coefficients for this. xk equals 1 over p. What's the interval you pick? So this is p. I'm assuming p is sufficiently larger than t that you don't have overlaps between adjacent ones. So if you do 0 to p, you're going to end up with an integral that you're going to have to split into two parts. 0 to t and then p minus t to p. That doesn't look too good. It's not wrong. It just involves more work. Minus p over 2 to p over 2, because if you do that, then you can actually limit the integral to what? Negative t to t. And you should do all this in your head before you even take pencil to paper. I'm going to pick this interval, minus p over 2 to p over 2. But it's 0 everywhere except this contiguous interval, minus t to t. And in that interval, the function is 1. So you have only e to the minus I k omega naught t dt. And I'm going to give you about a minute or two to tell me what that is. This is not a pop quiz. You can talk to each other about this problem. Okay. What have we got? Meatball.
So, the first thing I did, or we did here, is we changed the complex exponential into
You're telling me integrating a complex exponential is more difficult than a sine or cosine? E to the alpha t. Integrate. What do you get? E to the alpha t over alpha. What's alpha here? Negative k omega naught. And you've got e to the alpha minus I k omega naught t, negative t to t. So what do you have now? E to the negative I k omega naught cap t minus I k omega naught cap t over minus I k omega naught. Okay? So xk will then be, I can take the minus sign in the denominator, incorporate it in the numerator. I'll have 1 over p. I've got k omega naught, and then I've got e to the I k omega naught t minus e to the minus I k omega naught t. I have a difference of two complex exponentials. And I multiply the numerator by 2 and that by 2. Yeah?
In case when k equals 0.
Ah, yes. What do you do with k equals 0? Okay, so let's assume k is not equal to 0 and see where we get. Very good point. So I have in the numerator, I have 2 over, what's p times omega naught? 2 pi. Ooh, actually I didn't need to multiply and divide by 2. So let's keep that as 1. And recognize that this equals 2 pi. So I have a 1 over k pi times sine of what? K omega naught t. Okay? That looks like, if I draw it as a sinc, if I draw it as a function of k, it's going to be sinc-like. It's going to have all these values following a sinc envelope. Now we've got to worry about your concern. K equals 0. If k equals 0, what does my integral give me? T over? Or 2t. X 0 is 2t. And do I get the same number if I use Hopital's rule here? T. P. Yeah, 2t over p, sorry. 2t over p. 1 over p doesn't go away. If you use Hopital's rule here, you get exactly the same thing that you would get if you considered the integral as two separate cases. Okay? If this had been a continuous variable, where would the first 0 crossing be? If you replace this k with a tau, where would the first 0 crossing of this sinc be? So change this axis to tau and think of the continuous envelope. Where would the first 0 crossing of that be? 2 pi over? It would be when sine tau omega naught t is pi. So it's at pi over omega naught t. Okay? That's a measure of the width of this main lobe. It's inversely proportional to cap t. If you make t small in the time domain, what happens to the signal? The square waves become narrower. In the frequency domain, what happens to the frequency content? It gets wider. When you decrease t, the first zero crossing here moves out. That means the signal contains a larger and larger number of, or more of bigger frequencies. That's again the time frequency uncertainty. You make a signal narrow in time, you expand the frequency content. So this main lobe, as well as all the other zero crossings, will get wider and more separated apart. So you get bigger and bigger frequency content in the signal. Narrow in time, wide in frequency. That's a give and take between the time domain and the frequency domain. Now I want to know where my TAs are, because my script ends here. Bonsai!